Hey everyone, my name's Allan Heydon, and today I'm going to tell you about a machine learning technique based on label propagation that works with a very limited amount of labeled data. So this approach is called semi-supervised learning, and let me tell you how that fits in with relative to other machine learning techniques. So in this diagram on the left, I've shown supervised learning, which is the traditional machine learning approach, where all of the training data has a label. On the right, at the opposite end of the spectrum, we have unsupervised learning, where none of the data has a label, but we can use techniques like clustering to discriminate points in our data set. Semi-supervised learning falls in the middle, where we have a small portion of our data being labeled, typically much less than 10%. And actually, the techniques I'll be describing today, we can do learning with as little as 1 or 2% of our data being labeled. So to label the unlabeled instances, what we're going to do is use the context around each of our points. And the way we're going to do that is we're going to define a similarity relationship between the points. Where the idea is we'll say that two nodes are similar if they should have similar labels. And the way we're going to model the similarity relationship is with a graph. Now this graph, as we've heard earlier in the day, can take the form of either natural relationships, like in a social network, we have natural relationships between people, or it can be computed from the features of our points. 17 years ago, there was this landmark paper published that introduced this idea. This paper talked about using matrix operations for solving a system of linear equations based on the Laplacian matrix. Unfortunately, that doesn't scale very well. Their data sets consisted of only up to a few thousand nodes in that paper. And we aim to do learning on a many orders of magnitude larger scale. And so instead of solving these linear equations with matrix operations, what we're going to do is use an iterative approach that approximates it, and we're going to propagate labels along the edges of the graph. So let's walk through a simple example. Here I've picked out some of the training instances used in the MNIST handwriting recognition data set. Some of them are 4s and some of them are 9s. So we start out with our data instances, and then we're going to define the similarity relationship on the data points. And so I've drawn edges to represent the similarity graph. I've used the thickness of the edge to denote the degree of similarity. So the edges in our graphs will be weighted with a weight from 0 to 1. And then the next thing we do is we get labels for a small portion of our data. So here I've labeled 2 of the nodes. We call these seed labels because we're going to grow the set of labels out from the seeds. And I've indicated in parentheses that each of these seed labels has a weight of 1.0. So now we start the iterative process. On the first iteration, we will spread the labels from the seeds outwards along one edge. So that does a 1 hop of propagation. And then in the second iteration, the labels spread to the next layer of nodes. And now, after just 2 iterations in this graph, every node has at least 1 label. But if we keep propagating, you'll notice that the 2 nodes in the middle there end up with a label of each type. And that's because they are getting signals from their neighbors, some of which are 9s and some of which are 4s. So you can see with this technique, we can learn labels for all the nodes in our graph. As this example illustrates, there's a very simple interface to this label propagation system. It takes 2 inputs, the set of weighted edges defining our similarity graph, and the set of labeled vertices, and it spits out the labels that we learn at each node. One thing I didn't really illustrate in the example is that we can break our ground truth data into 2 sets, the training set and the testing set. We call these the seed and validation labels. And so by holding out some of the labels in our ground truth set for validation, we can run label propagation from the seeds and then measure how well the learned labels agree with the ground truth data at the validation nodes. And that allows us to compute lots of metrics about our learning, like precision and recall. One thing to note is that we won't necessarily learn labels for all of the nodes in the graph because, for example, if some node isn't connected by any path to a seed, there's no way a signal can reach the node. And another thing I'll mention is that often this label propagation can be used as a precursor to doing some sort of downstream learning. In that case, we can use thresholding on the nodes, on the weights of the labels that to pick out the nodes that we have the most confidence in what we've learned. Now, because this approach is so general, it has lots of different applications. I should mention that we don't really, the propagation, as I illustrated it, doesn't really depend on the meaning of, say, the image, those bitmaps. It just depends on the label weights and on the edges of the graph. So, for example, at Google, we've done, we've applied label propagation to spam and abuse detection, which is typically modeled as a binary classification problem, although it can also be modeled as a multi-class problem if, for example, there's different types of spam or abuse that you want to try and identify. We've also applied it to text and video classification, where there could be a very large number of potential labels. Another thing you can use this for is cleaning noisy labels. So imagine that we have some sort of guess for many of the labels for a lot of our nodes, but we don't have very high confidence in those. We can use the ground truth data that we have confidence in, propagate it around the graph, and then compare those learned labels to our noisy or uncertain labels, and weed out or delete the uncertain labels that don't seem to agree with what we learned. We can also use this for natural language processing. We've applied it to both sentiment and emotion classification. And also we've used it to improve recall when we are matching queries. We can expand or find phrases that are near synonyms of other phrases to improve recall on search. And lastly, as I mentioned, you can use this as a precursor to downstream, more traditional, like supervised learning. One nice thing, because we don't really, the algorithm knows nothing about the actual data instances themselves. It just knows about its neighborhood, and it knows about any ground truth labels associated with it. We can apply this to nodes that either have homogeneous type or are different types, so we can accommodate the heterogeneous case. The similarity relationships represented by the graph edges can be of different types as well, so long as we, adhere to the idea that similar nodes connected by an edge should have similar labels. And the way that we identify the nodes and the labels themselves are just arbitrary strings, so that's very general as well. As I've hinted, we can handle binary, multi-class, and multi-label situations. In the multi-label case, we can actually, we're trying to potentially identify multiple different categories for a single instance, and we can have multiple seeds for a single instance in that case. We also can accommodate negative label weights as well as positive ones. So for example, to do binary classification, we often have a single label with negative weight for the negative instances and positive weight for the positive instances. Our system has a pluggable algorithm for the update function that's used during the iteration. It defaults to a weighted average, as I'll explain soon. And this can all be used as part of a much larger machine learning pipeline. Typically, we do graph building beforehand, and we may do other kinds of post-processing steps once we have the learned labels. Importantly, our system scales to very large graphs. We've done runs with over 1 trillion graph edges with hundreds of billions of nodes in the graph. And we can also accommodate a very large label space on the order of millions of distinct labels. And the way we can achieve that is we use a massively parallel computation model that involves doing the label propagation on thousands of machines. One optimization that we use that's described in one of our papers is to not keep all labels at every node. We keep only the top K labels at each node. And we've shown that still produces good results. That's especially useful when you have a very large label set. So I've already described that we do label propagation over the graph, and we use an iterative algorithm. And the goal of this iterative algorithm is to minimize a loss function. The loss function shown here has three high-level components to it. One is, on the left, the label loss, which is for the nodes that have ground truth associated with them. We compare the learned label. We try and minimize the difference between the learned label and the seed label weights. The middle term is the neighbor loss, where we compare our labels. We try and minimize the difference between our labels and those of our neighbors. And that's proportional to the edge weight, and also is controlled by this neighbor penalty factor, mu NP. Finally, there's a prior loss, which compares our learned labels against some prior. By default, it's the uniform distribution across all labels, but you can specify other non-uniform priors, and you can even specify different prior distributions of your labels for each node if you so choose, if you have that information. So to minimize this loss function, we actually compute the weights at each node as a linear combination of the seed labels, if there are any, the labels of our neighbors proportional to the edges, and the prior label distribution. A variation on this technique is to take the features of the node into account. And to do that, we will train a model, typically either a decision tree model or a deep neural network. And the advantage of that is that we can leverage the power of nonlinear models. So the algorithm's a little different in that case. We first have to do a short label propagation run to generate training data, so we have some neighbor labels to train on. And then we train a model using the neighbor labels of the seed nodes as well as the features of the seed nodes to train a model. And we compare, when we're training that model, we use the seed label as the target label to train against. So in conclusion, label propagation is a very powerful semi-supervised learning technique that requires only a very small portion of your labels to be, your data to be labeled. It makes use of a similarity graph to propagate labels between neighbors. And we have a system at Google that scales to very large graphs and can be, and also large label spaces. And because it's a very general technique, it can be applied to a very wide variety of problems. We have made our system available as a Google Cloud AI workshop experiment. And if you search for semi-supervised learning with graphs, you can find that experiment on the internet. My last line here is just a link to Google AI blog post that we've written that describes this system in more detail. So thanks for listening.